Hey everybody, how you doing? Mr. Elliott here. I'm looking at my face and I'm like, man, it looks like Elliot's suffering from a cold. But honestly, I'm feeling better. I'm getting a lot better. I can breathe. I still can't taste food, but I can breathe. What we're going to be doing today is rationalizing the denominator. The main point of this is what do you do when you have roots on the denominator? And the rule of thumb is no, or not roots, imaginary. The rule of thumb is you're not allowed to have imaginary numbers on the denominator. And to understand what you need to do with roots or imaginaries on the denominator, it's good just to start with, well, what do you do when you have a square root on the denominator? Because it's the same rule. You cannot have a square root on the denominator of a fraction. It's just the rule. I don't know why that is. It just is. But you can get rid of a root by multiplying it by itself. So if I multiply this by root 5 over root 5, that denominator will just become root 25, which in the next step will become 5. And now that denominator is clean. On the numerator, 5 times root 3 is 3 root 5, and root 2 times root 5 is root 10. So at the end of the day, I have 3 root 5 plus root 10 all over 5. And I like my answer like that. Some people would break it up into 3 root 5 over 5 plus root 10 over 5. I don't care. I think both answers look phenomenal. Okay, moving on to number 2. Now, number 2 is a little bit more complicated because it has this 6 plus root 3. If you try that same tactic, 5 over 6 plus root 3, if you just multiply by root 3 over root 3, this is the wrong thing to do. Don't write this down. I'm writing this on separate paper because it's wrong. If you try this, the denominator becomes 6 root 3 plus root 3 times root 3, which is just simply 3. You still have a root on the denominator. You have not improved the situation. So just multiplying by root 3 won't work. So what we're going to do is we're going to multiply the top and the bottom by something called the conjugate. Class, can you say conjugate? Conjugate. All right, good job. What the conjugate is it's just like 6 plus root 3, but instead of being 6 plus root 3, it's 6 minus root 3. So we're going to multiply the top and the bottom by 6 minus root 3, which is the conjugate of 6 plus. If I would have said 6 minus root 3, the conjugate would have been 6 plus root 3. The plus, the minus, that's what it means by the conjugate. Numerator, 5 times 6 is 30. 5 times negative root 3 is negative 5 root 3. Now, the denominator, you multiply the firsts and you get 36. You multiply the outers and you get negative 3 root 6. You multiply the inners and you get plus, oh wait, I made a mistake. It's plus 6 root 3. Or minus 6 root 3. And then the inners is plus 6 root 3. And then the lasts is negative, positive times negative is negative. Root 3 times root 3 is root 9, which just becomes 3. And then on that next step, the denominator is still 30 minus 5 root 3, but then on the denominator, negative 6 root 3, positive 6 root 3, those just cancel out beautifully, and 36 minus 3 is 33. That's it. That's our final answer because we've gotten rid of the denominator and we have this the numerator up here like this. If you want to break it up into two things like that, you can, but I normally just leave my answer together. Okay, now, one thing. The whole purpose of the conjugate is that when you do the conjugate, the outers and the inners will always cancel out. So when I do these problems, I actually don't normally put this step in there. I just go the firsts minus the lasts keeping in mind that the outers and the inners are just going to cancel out. Okay, and I'll demonstrate that here. The conjugate of 3 minus root 5 is 3 plus root 5. So we're multiplying the numerator and the denominator by that. The numerator, 6 times 3 is 18. 6 times root 5 is 6 root 5. And then on the denominator, the firsts is 9. The lasts, negative root 5 times positive root 5 is negative root 25, which just becomes minus 5. And then the outers and the inners cancel out. Let me demonstrate. Positive root 3 root 5, negative 3 root 5. They're going to cancel out, so you don't need to include them in your work. Next step, 18 plus 6 root 5. Well, that's a number. That's a root. They don't add together. So that stays like that. But 9 minus 5 is 4. And now I notice this one actually has one more step of simplifying. What divides out of 18, 6, and 4? They're all even, so a 2. And it becomes 9 plus 3 root 5 all over 2. Very nice. And I like to leave my answer like that, though you can break it up into 2 parts like that. So that's multiplying by the conjugate. If you like to show, if it helps your brain to show this step here where you multiply, where you do the outers and the inners and then you cancel them out, you should show this step. But just know, you can recognize that if you multiply by the conjugate by itself, like this here, the outers and the inners will always cancel out. So that's square roots. Next we're going to move into imaginaries, but imaginaries work out the exact same way. By multiplying it by, the problem here is this I. And we know that I squared is negative 1. So if I multiply the numerator and the denominator by I, 7 times I is 7I. Denominator 2I times I is 2I squared. I squared becomes negative 1, so this becomes a negative 2. So I get 7I over negative 2. And you could leave your answer like that. You could change it so that it's negative 7I over 2. You could put the negative on the numerator. Doesn't really matter. The answer is still the same no matter how you look at it. I prefer one of these two answers. I don't normally like having a negative on the denominator, but it is mathematically correct and you'll get it marked right. Side note, a lot of people just like to think about it like this one, that you're going to multiply, that you want to multiply it by itself. If you would have gone 7 over 2i times 2i over 2i, you can do that, but it's going to give you an extra step in your work. 7 times 2i is 14i over 2i times 2i, which is 4i squared, which becomes negative 4. Now this is even and that's even, so then I divide everything by 2, and I end up with that exact same answer on the next step. So you can do this if you want, but it's a little extra work. Boop, example 2. So using that same idea, you have an I on the denominator, so you're going to multiply the numerator and the denominator by I. Like I just said, if you want to multiply by 5i, you can. 3 times I is 3i. 2i times I is 2i squared all over 5i squared. 2i squared becomes negative 2, so 3i minus 2. 5i squared becomes negative 5, and then needs to be in complex form. So it means you need to have the real first, negative 2 plus 3i all over negative 5, and in proper complex form, this is not an acceptable answer. Negative 2 divided by negative 5 is positive 2 over 5. Positive 3i divided by negative 5 is negative 3 is minus 3i over 5. That is the proper answer. I know that I said in quadratic formula I would accept this answer, and I will accept this type of answer when you're working quadratic formula. But in a problem where it's telling you to rationalize the denominator and answer in complex form, you should answer it like this. All right, now check these out. 3 plus 2i. If you think back to what we did in part 1, multiplying by its conjugate, the conjugate also applies to imaginaries. What? It does. So the conjugate of 3 plus 2i is 3 minus 2i. So I'm going to multiply the numerator and denominator by 3 minus 2i. I'm going to show all my work on this one, but on future problems, I'm going to back off on that a little bit. Numerator, 4 times 3 minus 2i. 4 times 3 is 12. 4 times negative 2i is minus 8i. Denominator, firsts, 9. Outers, negative 6i. Inners, positive 6i. Lasts, negative 4i squared. Then, just like the square root problems, check out those outers and inners. A negative 6i, a positive 6i, they straight up cancel out. So I'm left with 12 minus 8i all over 9 minus 4i squared. That 4i squared, the I squared becomes a negative 1. This becomes a negative 4, which ultimately makes this plus 4. So 12 minus 8i all over 9 plus 4, which becomes 12 minus 8i all over 13. And then to finish it off, 12 over 13 minus 8i over 13 to get it into proper complex form. Now, the outers and the inners will always cancel out when you multiply by the conjugate. So for my future steps, I'm just going to jump straight down to here, where I'm just going to go 9 minus 4i squared. And then I'm also going to skip this step because I know that negative 4i squared becomes 9 plus 4, which would become 13. So on future work, I personally don't show those two steps. I go straight from here to here, and then I go straight from here to here, and then I go to my answer. And that's what I'm going to do on this one. I have a denominator of 5 minus I, so I multiply by its conjugate, which is 5 plus I. On the numerator, 8 times 5 is 40. 8 times I is 8i, so it's 40 plus 8i. Denominator is you do the conjugate thing, so which becomes 20. The firsts is 25. The outers and the inners, positive 5i, negative 5i, they cancel out, so I leave that out. And then minus negative I times positive I, that's negative I squared. This becomes 40 plus 8i all over. This becomes positive or negative 1, which makes this 25 plus 1, which is 26. And then to get into proper complex form, you have to break it into two things, and you have to simplify. I notice that all three of these things are divisible by 2. So the 40 becomes a 20. The 26 becomes a 13. So I have 20 over 13 plus 4i over 13. And that is my answer, A plus BI. All right. I have one more example for you. This is as complicated as they get examples. 3 minus 2i times 6 plus 5i. Same thing. You multiply it by its conjugate, 6 minus 5i over 6 minus 5i. Denominator becomes 36 minus 25i squared, which in the next step becomes 36 plus 25. Numerator I need to be a little bit more careful of. You have to do the complete foiling for this because you're not just multiplying it by its conjugate. This trick of the outers and inners canceling out only works with the conjugate. Firsts is 18. Outers, negative 15i. Inners, negative 12i. Lasts, positive 10i squared. The positive 10i squared becomes negative 10. The negative 10, when I add it up to that 18, becomes 8. Negative 15i minus 12i is minus 27i. So on my next step, oops, sorry about that, I have 8 minus 27i all over 36 plus 25, which is 61. That's not going to simplify. I think 61 is a prime number. So my final answer is 8 over 61 minus 27i over 61. That's it. I know I worked horizontally this problem. It's not normally the best form, but it is a technique. I know I usually complain to students about it. Maybe I shouldn't have done it there, but I did. Okay, students, that's it. I hope you have yourselves a beautiful day, a beautiful night, wherever it is in your life. Let's hope it's beautiful. I'll talk to you later. Bye-bye.